So it's exciting to be here. This is actually both the first computer science colloquium I've ever spoken at and the first one I've ever attended. My background's actually not in computer science. I know the mohawk and the tattoos give it away, but I'm a credentialed actuary. But at any rate, I've been working at MaxSeller for the last year, and I want to tell you guys about what we do at MaxSeller, and as Andy pointed out, what the paradigm is in computing that we're trying to introduce and essentially trying to overthrow. So I'll start off by answering that question of, what is it that makes processors inefficient, or what makes computers as we know them inefficient, because almost all computers that we know are based on processors of some form, CPUs, GPUs, microprocessors, that sort of thing. So the way I explain this at a cocktail party when I'm trying to give somebody who doesn't have a background, the 5-minute answer is, imagine the city of Chicago one day passes a really bad ordinance, and they say that all of the white-collar office work, all the lawyers and dentists and doctors and all the people that work indoors in Chicago all have to get their work done in the Willis Tower in one central location. Right? It's very much like the way we build processors now. We have a little tiny bit of silicon that's dedicated to compute, and everything has to go through there. But we have this problem that Chicago still has the same number of white-collar workers. Right? There's still all these people living all the way out in the suburbs. And in order for them to get any work done, they have to get all the way to the Willis Tower and back. Right? So being engineering creatures and human beings, we figure this out. And we say, OK, well, what we're going to do is we're going to bring all the lawyers in for 10 minutes. And they're going to get all their lawyering done. Right? And then they're going to have to go, and the accountants are going to have to come in for 10 minutes. And then what do we have? Well, we have a traffic problem. Right? So now we need to start building triple-decker highways and thinking of all these different ways of getting all of those people to and from the center without colliding with each other. Right? And at some point, some enterprising developer thinks, oh, well, I know how to solve that problem. I'll put in some temporary corporate housing that's really close to the Willis Tower, and people will sort of swap into it. If they know they're going to need to be at work the next day, they can stay in one of these high-priced apartments and get there more quickly. And that's basically it. Right? So, and that in my metaphor is like the L1 and L2 cache, that sort of thing. If I go and expand this city, I don't really get any more work done. Right? If I go add more houses to the edge of it, it doesn't really get more done because it all has to go through that central point. And the only real idea we have for getting more work out of this kind of a system at this point in computing is just to copy and paste. Right? So we put multiple ALUs, multiple cores on a chip. And by doing that, sometimes we make them smaller and weaker like we do in a GPU. But the basic idea is we just can't squeeze any more power out of one processor, so we start adding cores. Right? So what's happening now in computer science is that Moore's law is still with us. We're still packing transistors on a chip exponentially. We're still doing that. What's failing now is frequency scaling. Right? Those individual cores that we're building are no longer getting that much more powerful with each generation the way they used to. So instead, the only way we can get more performance is just by putting more of them on a chip. And the problem with that is that performance doesn't come free. Right? It used to be that if you wrote code and a processor came out that had double the clock frequency of the last processor, you could compile that same code for that processor and run twice as fast. We don't get that kind of free performance anymore. Now you have to expose that parallelism in your code. Now the reason we do all of this is in service to one of the oldest ideas in computing, right? The control flow model. And in the control flow model, which is, by the way, every kind of programming pretty much I'm sure all of you have ever done. Right? If you've ever done Python or C or doesn't matter, whatever language you worked in, you were doing the control flow paradigm. And in the control flow paradigm, we treat data like it's static. It lives out in the suburbs. It has a picket fence and an address. And when I want to go get it, I go get it, I pick it up, I do work with it, and I put it back where I found it. We treat instructions like a kind of data. Right? So instructions are just a sequence of data that we go through in time to actually do our computing. We call that computing in time at MaxSeller. Now, what this means is that the actual silicon on the chip, there's a lot of stuff that has nothing to do with compute. Instruction decoding, caching, fetching, all of that. Machinery has to be there, and it doesn't actually do any real work. It just moves data around. Right? So it's an inefficient way to solve any problem, but it has a great sales pitch. It's an inefficient way to solve any problem. Right? It's really easy to take. I can take a 10-year-old kid and teach him to write Python and do stuff in Minecraft. They're doing that now. Right? I certainly can't take a 10-year-old kid and teach him how to build a flip-flop. Right? So hardware design is hard. Software design is easy. This model has worked up until this point, but we're running into fundamental limitations of the hardware. At MaxSeller, we promote a different model of computing, what we call the Dataflow Model. Right? This is also a very old idea in computer science. It was just never really realizable in a real way until more recently. In the Dataflow model, instead of treating data like it's static, we treat data like it's moving constantly. And that means all of that machinery that is to go fetch data and bring it back, that goes away. We don't need that anymore. And instead of computing in time by running through a list of instructions, what we do is compute in space. We take the actual physical surface of our silicon, we arrange the compute we want to do in space across it, and we flow the data through it to actually do the computation. Right? And the advantage of this is we're not wasting silicon on machinery that doesn't actually do work. Right? So we can squeeze a lot more compute into a little tiny chip. And we're also not wasting clock cycles. Right? So if I write a piece of code and I want to know how fast it runs in a control flow system, there's only one way to know. That's to actually run it. Because there's all kinds of variables I don't know about, the operating system, the caching. I go get something from data. Maybe that takes 10 cycles if it's right there in a cache. Maybe it takes thousands if I have to go and get it from RAM or even from a disk. Right? So in a Dataflow model, the very next piece of data is going to arrive with the very next clock cycle. So every single clock cycle gets used to compute. So I'll tell you a little bit about MaxSeller as a company. Right? MaxSeller began here at Stanford with our founder's research in the late 90s. He completed his PhD in 2000. Was that under you, or was that just you were? Mike Flynn. OK, it's under Mike Flynn, who is now one of our chairman of our board. You take the credit but not the blame. OK. So it started here at Stanford. I took it to Bell Labs for a couple years and then bought out his research project and started a company, MaxSeller, in 2003. We have had clients in oil and gas, Chevron, Eni, Schlumberger. We've had clients in finance, JP Morgan, CME Group, Citigroup. We also have clients in defense and cybersecurity. And we have a number of strategic technology partnerships with companies like Juniper, Hitachi, and AWS. So I'll tell you about a couple of our commercial success stories real quick with this technology before we dive into how it works. So one of our earliest ones was with Chevron. Chevron takes these big boats out, and if you see this boat, it's trailing thousands of seismic sensors. And they take it out, they shoot an air gun into the water, they get feeds back on all those sensors, and then they have to run a really big 3D finite difference model to basically piece out from that data where the oil is. What they were doing was taking this boat out, shooting things, collecting a whole bunch of data, sending it back to a data center, processing it, getting it back. And of course, the boat by that point is no longer over where it was. And if you want to turn it around and go survey the same area, it's a big overhead to do that. So we actually worked with them to develop Dataflow as a way to address that performance density problem, to bring more compute as close as possible to where this data is being actually collected. Another client of ours, JP Morgan. In the financial crisis, as I'm sure many of you know, right, complex credit derivatives were very hard to compute during the financial crisis. People didn't care before the financial crisis because they were seen as having no risk. But afterwards, it was a big deal. We stepped in with JP Morgan and took one of their risk calculations from 8 hours to 2 minutes on our boxes. So they were also very happy with us. And then finally, Juniper Networks. This is one of our technology partnerships. We've actually released a commercial product with them, the QFX 5100. This is a top-of-rack switch. So in a data center, you've got a rack of servers. And at the top, generally speaking, all your connections go through a top-of-rack switch that then goes out to the rest of the network. We have a top-of-rack switch with one of our Dataflow chips in it that can be programmed using our software. And basically what that does is if you're a data center, you have data coming in, and you need to do some kind of compute. If maybe you're a bank, you need to do risk metrics. Maybe you're some kind of institution that has regulatory requirements where you need to timestamp packets, things like that. We can capture that data and process on it at line rate. As fast at 40 gig E, 100 gig E, whatever's coming in, we can process. So how do we build this? How do we actually build a Dataflow computer? And so for the next section, I'll kind of talk you through the process, and then I'm going to go through a specific example that I've actually worked on. So it starts by understanding our algorithm. This is really the biggest thing at MaxSeller, right? Control flow is how 99% of all programming works. It's how 99% of all programmers think. And in order for me to take my problem and build a Dataflow computer around it, the first thing I have to do is rethink the problem in terms of Dataflow. That's really where most of the work goes in. It's where the thought work goes in, right? Thereafter, the technology takes over. So this is really the tricky part. Once I understand my algorithm, the next thing I'm going to do is I'm going to start writing in our Java-based language, MaxJ. Right? So whenever I tell people this, they look at me and go, "You do high-performance computing in Java? Are you nuts?" Well, no, we don't actually run the Java, right? What the Java does is it describes the calculation we want to run. And then when we run that Java, it builds the computer that does that calculation. So the Java itself is not actually what we run at runtime. It's just a design language. That's all it is. Once we've designed written the Java, we can put that into our Max compiler, which runs that Java and assembles the graph. And what we get is a Dataflow graph. So this image over here on the right, and I'll go into this in a little bit more detail in a moment, but this is what we call a Dataflow graph, right? It has inputs at the top, operations, and then it filters down to an output at the bottom. What I can do with that data flow graph once I've assembled it is I can run it as though it were an actual computer. Now I'm only simulating, but if you've ever played with a hardware simulator, you simulate a lot of things, right? You simulate bit by bit, signal by signal, clock switch by clock switch. I don't have to do nearly as much to simulate a graph, right? If I have a graph that says add two things together, all I have to do is loop through two arrays and add them together. It's much easier to simulate. So I write my MaxJ, I build my graph, I test my graph, and then I have all the standard software development tools. I can do debugging, I can do unit testing. If I don't like what it does, I go back and I write some more MaxJ, and I keep doing that until I'm happy with the code that it's running in simulation. Once I'm happy with the code it's running in simulation, then I'm going to take it and run the hardware build, and the hardware build's intensive.
So are you supporting any other languages besides Java?
At the moment, I don't know if we have full support for any language, but the plan is to skin whatever language people want, right? I mean, we can do it in Python. It's easy to put skin layers on top of that.
And you're not doing anything like taking the Java and, say, compiling it to C, then having a separate C?
No, we're just building an object model. So I'm building a graph. I don't care how efficient the memory model is or any of that, because it's not what I actually run. I just need to be able to build a model of objects and the connections between them.
Are your data flow graphs static or dynamic?
Well, they're static because they get burned into the chip, basically, right? So the data moves dynamically through them, but I can't take my graph and the chip that I've already burned, basically, or a chip that I've already laid it onto, and then say, hey, I want a mux there, right? I mean, I can do that in code, but it's a lot, I have to go through the hardware build process again to actually get it out. So I take a little bit more of a close look at what that actual coding language looks like, right? So this is a very simple example. What I have is a very simple calculation where I'm taking a stream of data in at the top, and I want to do a moving average, right? So I have a stream of data, and I want to take 3 adjacent elements, add them together, and divide by 3. Really, really, really basic. So the way I need to do that in code is I start by defining an input. So I have this first line up here, x equals io.input. And that creates that little house at the top of my data flow graph. It's just saying I have an input. And thereafter, I just have lines where I create new variables from the old variables with formulas, equations, multiplications, additions, all the standard things that I would have in the scientific code or the engineering code, whatever I was copying over, right? Any kind of formula, I could pretty much copy and paste it into Java. Right? But what I'm doing with those calculations is when I run this, it's not actually, there's no number there for prev and x and next and things like that. It's building this graph. It's saying that these things, saying prev plus x plus next equals sum, means that those 3 lines have to be connected by addition operators to come out with a new line, that sort of thing. Very much like TensorFlow, very similar concept, right? So if you've ever worked in TensorFlow, you start with this sort of tensor object, and then you do operations on it, you get other tensor objects. That's effectively what this is, right? So very, very similar kind of concept. And what's nice about this is because it's code, and because it's object-oriented code, so I also have the advantage of polymorphism and whatever other kind of sort of tricks I want to play, I can build really complex graphs with relatively simple code. So this is a graph, this is 4,600 nodes in a graph of a 3D finite difference time step. Now, if I showed you the code that generates this, you'd be able to read it. It'd be, this element plus that times this. It's a formula, right? But when you actually expand out all the different data dependencies and connections in that graph, it's a very big, complicated graph. And we can build that with very simple code. That's really the benefit of MaxJ and the Max compiler. So, OK, now we've got our graph. We know the calculation we want to do. Now I need to actually physically build a machine to do it. Right? Up to this point, all I have done is abstractly defined a machine. Right? And that's important. That's really where the most of the effort goes into, is abstractly defining my data flow computer. But how do I actually get performance out of it? How do I actually build it? So the first thing I need is an actual physical representation of the data flow graph. So I need a chip. And on that chip, I'm going to have the silicon actually arranged into, so for example, the individual compute nodes will be pieces of logic, right? And then the lines connecting those nodes are actual wires that flow the data from one of those centers of the silicon to others. Right? So I have an actual physical representation of my data flow graph on my data flow chip, and that's what my data is going to flow through. The rest of the data flow engine is places for the data to flow to and for the data to flow from. So for example, one place I might want to flow data to and from is from PCIe. Right? So I want to be able to talk to a CPU that's running basically like a C, just basic C code. And I want to be able to send data to the card and get data back from the card, just like I would with any kind of accelerator, right? So I have PCIe Express. I want to talk to it, and we have an API called Maxeler OS that handles all of the low-level details, all the driver and the individual running of pins and all that. So you literally say, here's my data in CPU memory, run this calculation on it. Very, very basic. Another place I might want to have data flow to and from is memory on the actual board. So I'll talk a little bit about our memory hierarchy in a minute. We call this LMEM, right? Large, these are usually DDR4 DIMMs. We can fit, so like the latest generation, we fit 3 of them on a board. We could do 32 gigs, so that's like 96 gigs, for example, of potentially RAM. And again, that goes directly into the chip. So there's a little different than other accelerators, right? The CPU does not talk to that memory. It talks to the chip, right? And the chip talks to that memory. And I can implement the memory controller on the chip, and that's how I can get data to and from memory. But it all goes through the chip. Another thing I might want to do is talk to other DFEs, right? If I can't get all the work done in one Dataflow engine, then I want to communicate with other ones. I need an interconnect. The latest generation, that's an optical interconnect. It's a bidirectional interconnect to 2 other cards. So I can do like a ring topology, for example, where I could put 4 cards in a ring, and each one can communicate out and back to its 2 neighbors nearest to it in the ring. Right? So, and again, that goes straight into the chip. That's not mediated by an OS or a CPU or anything like that. And then the last thing I might want to do is talk to a network. So I can actually put an external QFSP on the board, and I can put 10 giggy, 100 giggy, basically whatever I can buy the IP core for, right? Because they cost more money for 100 giggy. But then I can take network traffic. Either I can capture like TCP/IP traffic, or I can talk to network storage. All of that at a much higher rate than I get from the PCIe. So generally when people come to us and they say, I've got data and I want to get to it faster than I can get through PCIe, network is usually the next place we'll go for that. So this is what one looks like in real life, right? This is a box that we have. This is a 1U blade. So if you've been in a data center, 19-inch, some odd wide blade, it's about 1.5 inches high. 8 of those cards will fit in it. So why 8? I mean, you certainly can't fit like 8 GPUs in a 1U blade. And the reason for that is these things operate at very low frequencies, 100, 200 megahertz. They generate very little heat. The cooling system is literally, it's just a block of copper that we blow air over. There's no water, none of that fancy stuff, right? So we can stack a lot of them in a very small space. That 1U blade will hold 8 Dataflow engines up to 1 terabyte of RAM, split out among those Dataflow engines. All of them, of course, interconnected to each other with that max ring interconnect. And then we also have what's essentially a virtualized PCIe connection, right? So I take this thing, I put it in a big rack, I connect it to an InfiniBand switch, and then if I have a CPU node connected to that InfiniBand switch, I say to that, on the CPU node, I say, here's an IP address, give me 4 DFEs. And this thing will allocate me the DFEs and then map them as though they're just available via PCIe. So in these, generally we say like in the equivalent performance to 20 to 50 x86 servers. It's hard to gauge performance, and we'll talk about this as we get into it later, because it just depends on the problem, right? For some problems, it's going to be a massive improvement. Some it's going to be more moderate. So it really just comes down to what the problem is that we're trying to port. That's why there's a wide range on that number. So I'll go through a specific example, right? This is one I've been working on for the last year or so. Quantum Espresso. This is part of a larger project for PRACE, the Partnership for Advanced Computing in Europe. And they've asked us to port 4 applications. This is the one that was assigned to me. Basically what this is it's a Fortran, it's an old Fortran software package, or a series of Fortran software packages. Yes, I had to learn Fortran for this exercise. That was fun. I actually don't complain about it too much. What it is, I won't go through all the physics and the details of the calculation, but basically it's an iterative solve. I have this really large system. I need to do a whole bunch of linear algebra and FFTs, and I'm going to start with a guess, and I'm going to iterate until that guess converges to some fixed point, basically. The reference that they gave us was a system tantalum oxide, and it took 2 full racks of Blue Gene Q. So if you've ever seen Blue Gene, I mean, these things are the size of a refrigerator. It took 2 of those, 6.7 cubic meters of space. And I looked this up, by the way. A typical domestic refrigerator is about a cubic meter. So that's 6 or 7 refrigerators worth. 32,000 cores, 53 minutes of wall time, and it used 384 kilowatts of power. And by comparison, like a typical house is a couple of kilowatts. So it's the size of a couple of refrigerators uses a couple kilowatts. Can we beat that? So the first thing we do, right, we unpack our Fortran software package, and we start doing what you do with any kind of software you're trying to improve. We profile it, right? So For Dataflow, we're looking for something a little bit different. Most profiling tools focus on function calls, right? Function calls are a control flow concept. I have a sequence of instructions, and what a function call basically is a jump to kind of instruction, right? You're at this point, go to that point. So that means I can have reusable logic. I can have some section of code that I can run over and over and over again, and it runs essentially independent of the context it's called in. I could run it 1,000 times, I could run it 1 time. It doesn't know. It's just an independent piece of logic. That's control flow. We don't have that advantage in Dataflow. In Dataflow, we think about loops. Right? We think about the major loops, the order that those functions get called in, and we think about the amount of data that flows into and out of those loops. So we generally build something like this. This is a loop flow diagram for quantum espresso. Again, I won't go through the physics, but the basic idea is there's really 3 major loops in this program. And if you go through the functions, you'll find them eventually, right? There's one loop, and then, OK, the other loop is in a function that it calls and that kind of thing. But once you've mapped out the logic, it's really easy to see how the program itself actually works, right? So in this case, for quantum espresso, we focused on that innermost loop, that FFT loop, right? So this outermost loop runs a couple dozen times. The middle loop runs a couple hundred times. The inner loop runs a couple thousand times. And one of the things we notice about the inner loops has 2 inputs, has the psi input and the VRS input. And it turns out the psi input is pretty big. The VRS input's pretty small, and it doesn't change very much. So those are just really big, positive things for acceleration. The other thing is that if you think about the amount of internal memory it would have to generate to run through that whole 5 gigabytes, it'd be something more like 250 gigabytes. Now, in real life, you wouldn't really allocate that. You'd break it into little pieces. But if you think about that as like a total memory requirement, it's a lot more memory in the loop than going into and out of the loop. That's a prime indicator that it's a key target for acceleration. So again, on a control flow system, we'd break that into batches. We'd say, all right, here's my 5 gigabyte problem, break that into a bunch of 100 megabyte problems, move the 100 megabyte problem into memory, do everything I need to do, grab the result back, then move the next one. It's a shift kind of thing. For Dataflow, I run all of them at once, right? I just run the first one, and I just keep going. So once I've done my loop flow graph, the next thing I need to think about is where I want to actually put things in memory. So I talked a little bit earlier, we have a 2-tier memory hierarchy, right? We have FMEM, which is memory that's on the chip, the fast memory, right? So I tell people this is kind of like L1 cache. I mean that only in terms of speed. It has the speed of L1 cache. It's not a cache in any kind of sense. What it is allocatable memory units on the chip that I can grab, that I can put an address on them, and then I can pull data out of them every clock cycle. So every single clock cycle input can pull memory from a different address in my FMEM. So there's no like, OK, I send out the request, and then I wait a couple hundred cycles, and then it comes back. It's literally just this cycle, that data, the next cycle, that data. There's also LMEM. LMEM is those onboard DIMMs. And for those, obviously, I have communication. I have to go through a memory controller. I have to talk to the DIMMs. I have to get the data out. And so for that, obviously, it's slower, but it's much larger. I can fit up to 96 gigs. And that's it. It's a much simpler memory hierarchy than, say, a GPU. So in quantum espresso, for example, this cube that I need to do 3D FFT over, there's a cube, and I'm basically going to do 3D FFT, do a multiplication, do 3D FFT back. And if I look at it from a Dataflow perspective, I'm going to need to do 2 things. I'm going to need to do all the multiplications and additions and everything that goes in the FFT. That part is easy, really, really easy. It's multiplications and additions, right? The other thing is reordering the data. I have to reorder the data within the FFT, and then I have to reorder the data when I'm doing transposes. So for example, if I have a plane and I'm reading across it one way, I have to store that in memory and then read it out the other way. Okay? So where I do those transposes depends upon the size of my memory. The plane that I would need to do the 2D transpose on is about 0.5 megabyte. I've got 40 megabytes available on the chip, so obviously I'm going to do all those transposes in FMEM on the chip. The whole cube itself is too big to do that. The whole cube's 128 megs. So when I want to do 3D transposes, which is where I've basically reading the cube like this, and then I have to read the whole thing in before I can start to read across it in the slow dimension, right? So for those, I have to actually send it out to LMEM and then get it back. I can't fit it on the chip. Another thing that I noticed, this is a really, really just fun problem for this particular type of thing, because I'm not starting with the entire cube filled in. I only start with a little sphere that's actually only about 5–6% of the total area of the cube. I'm going to FFT across the whole domain, but I only care about putting that sphere in, and I only care about the values that end up in that sphere on the way out. So that makes it a lot easier. It means that the amount of data that needs to move to and from the board is just about 6% of the cube. The amount of data that has to move to and from those large DIMMs is about 50% of the cube. So there's about 10 times more data that has to move to LMEM. That works out pretty nicely because the bandwidth between the DFE and LMEM is about 10 times higher than the bandwidth between the DFE and PCIe, right? So I have a sort of natural fit. Once I've identified where I want to put my memory in my data flow, then I start laying out my actual flow, my architecture, right? So in this case, for example, I'm going to start with my input data on the CPU. I'm going to feed it into the FFT in the first dimension. I'm going to do a transpose, and you see that's talking to FMEM on the chip. Then I'm going to go to the FFT in the second dimension. Then I have to go out to memory, get it back, do the FFT in the third dimension, multiplication, and then undo the whole process, right? Now, the thing you notice about this is that it's one continuous pipeline from beginning to end, right? So I have psi goes all the way out to h psi. So if you think about this like a pipeline, think about it like an oil pipeline, right? If I want to send a barrel of oil on an oil pipeline, I don't put one barrel in it, send it all the way to the end, and then once it gets out, put the second barrel in, right? I can feed data in as soon as the pipe is empty, even if data hasn't started coming out the other end of the pipe. So I could have the first cube go in and be working its way through down here somewhere and already be feeding the second cube's worth of data in. Right? So that's a huge advantage over control flow architectures where what I'm going to have to do is move the first cube's data out into memory, do everything I need to do, and only when everything is done and all my threads are synchronized and all that's happened, then I can move it back and start the second one. Here, it's a pipeline. As soon as the first one goes in, the second one starts going, even if the first one hasn't come out. The other thing that's nice, again, as I pointed out, the widths of these arrows indicate roughly how much data is flowing in and out. And you can see that there's a lot more data moving between the DFE and the memory than there is between the DFE and the CPU, and it matches the bandwidths, which is very nice. Now, again, if you think about this from a control flow architecture, I don't really control this at all. This is going to be dependent on what my cache can do, right? So I might have the same kind of bandwidth limitation, but I don't have the ability to use it in an extremely optimal way. So what does this look like in real life? That's what the chip actually looks like. When I take that data flow graph and I build it out, this is a tool we have called aerial view. And what this does is it takes every individual little logic cell on that chip and highlights it to indicate what part of the calculation it got put in. So if you go back to this architecture diagram, there's really 5 compute kernels, right? Those light blue circles. 1, 2, 3, 4, 5 compute kernels. And if I look at this picture, there's 5 shaded regions, 1, 2, 3, 4, 5. Those are those 5 compute kernels, right? Just in that thing on the left, and I'll show you what the other 2 are in a moment. So if I actually overlay the data flow on top of this, it makes a little bit more sense, right? So this shaded region up here in the top right, that's my first FFT. The data comes in from PCIe. The PCIe is not like literally on top of the chip. There's pins and things like that, but it's just for a diagram, right? Data comes in, and it goes around, goes to the memory controller, back out, goes to this kernel, and works its way back up. And all that happens literally physically in space. So all 5 of these regions are running all the time. And the only difference between what they're computing is what stage they're at. The ones that are later in the pipeline are doing later data than the ones that are before, but they're all working on data all the time, every clock cycle. Now, the other 2 sections of the chip, they're just more silicon, right? This particular chip comes in 3 pieces. They basically, the way they're building these now is they make a die and then they just kind of copy it 3 times, right? And they're called SLRs, is something single logic regions or something like that. There's 3 of them on the chip, and it turns out that when I do this whole pipeline, it fits in one of them pretty well. Which means what do? I just copy and paste, right? To go back to that old trick. So this now actually has 3 copies of that, and then you can't really see it from these diagrams, but the individual kernels themselves are actually double width as well. They handle 2 input streams and 2 output streams. So all told, this is actually 6 pipes. So not only am I doing every stage of the pipe simultaneously, but if I have 6 pipes, all 6 pipes and all stages in those pipes are running simultaneously. So what does it actually translate to in terms of performance? How does this actually perform? So first of all, we have to kind of caveat things, right? Which is that the way you think about performance in data flow is going to be very, very different than the way you think about it in control flow. In control flow, we think about performance in terms of runtime, right? I hit the button, I run it, I get an answer out at the end, right? The reason that works for control flow is we're reusing the hardware, right? So if I have one core, I run something, it takes 10 seconds, running it 10 times takes 100 seconds, because I can't reuse that hardware while the first one's running, right? So we think in terms of runtime. For Dataflow, we think more in terms of throughput. We think in terms of the rate at which it's processing the data. I think of this as, like, think of the analogy as like your water faucet at home, right? When you open your water faucet at home, you don't care how long an individual molecule of water took to get from the water tower to your faucet. That's completely irrelevant information to you. What matters is the flow of the water, how much water is actually coming out when you pull it out. So we have to think about it in terms of flow. And when we try to figure out the performance of one of these systems, we have to break out a very sophisticated technical tool called a pocket calculator. Right? That's one of the weird things about this technology is actually realizing the Dataflow computer is a lot of work, but estimating how it's going to perform is really trivially easy. And that's because I don't have any of the cache or operating system kind of overhead and mechanics and pieces that I don't understand in 15 different architectures I'm trying to support, and different compilers do different things. I don't have to worry about any of that. I know exactly how it works. I know exactly what the throughput is. So in this case, we think about that in terms of 3 potential choke points. Right? We think about that in terms of, first of all, PCIe. Right? I have to be able to move the data from the chip to the DFE. And that's a simple calculation. I sit down and I say, all right, every cube needs to move 7 megabytes of data. I can get 3 gigabytes a second. I do a simple division, 433 cubes a second. Right? Really, really, really basic. I mean, literally, it's an Excel spreadsheet that we do this in. Right? So the PCIe will move 433 cubes a second. I can do the same kind of calculation with the LMEM, right? The LMEM, I have to move a lot more data, but I have a lot higher bandwidth. And I work out the calculation, and OK, that one moves 250. The last piece is compute, right? I have to know how fast I can actually compute the data in between those 2 places. And so for that, I need to think about clock cycles and clock frequency. I need to know how fast, basically how many clock cycles it takes to do a cube and how many clock cycles I get a second. So it's easy to work that out. The FFTs consume 4 elements every clock cycle. There's 16 million elements in a cube, therefore 4 million clock cycles per cube, 150 million clock cycles a second, and then you multiply everything by 6 because there's those 6 pipes, right? So all the throughput is just multiplied by 6. And that comes to 215 cubes a second. So obviously it's easy enough to look at this and see where the bottleneck is. The minimum of these 3 things is 215, therefore my Dataflow computer will do 215 cubes a second. Now, I don't know how long 1 cube takes. Right? I don't know how long it takes to put in 1 cube and wait for it to come out. But I know if I have to run 200 or so, it's going to take about a second. Now, by comparison, how does the reference system handle? Well, that big refrigerator, the 6 refrigerators or whatever put together, 1 rack of Blue Gene, so half that system, does about 330 cubes a second. So this is 1 board, 1 PCIe backplane, that does basically half of what a full Blue Gene rack does. So if you kind of think about that performance scaled up to a full-size system, right? So this is a picture of the Blue Gene itself. 1 rack, 3 some odd cubic meters, so 3 refrigerators, roughly speaking. Power is 192, is half that 384. And that only does 338 cubes a second. For that 1U rack, remember, I can fit 8 DFEs in it. So if 1 DFE does 215, 8 of them do 1,700. Right? So it's quite a lot of, quite a lot in that 1U rack. But each board only uses about 100 to 200 watts, right, at most. So it's much lower power. Right? Remember, what is most of the volume of that Blue Gene? It's not silicon. Well, most of it probably is silicon, but there's also a lot of it that's just literally water. There's a tank of water in this thing that circulates through. Doesn't do any computing at all. It just is water, right? Everything in that 1U box is compute, every last little bit of it. So what you see over that is we don't need all the water cooling. We don't need all the communication. That's the other thing is if you look inside this Blue Gene, it's a ton of communication because that FFT is split out into 256 pieces. It gets done on 256 separate cores. We don't have any of that communication. They're optically connected, but I'm not actually using that for this. It's air-cooled. It's literally like a block of copper on top of a board. And it's just way more power efficient. So if you work it all out, it comes out to 700 times more efficient at this one task in terms of the amount of compute I can do per, say, cubic meter, and 1,000 times more efficient in terms of the amount of compute I can do per watt. Right? Now, the big caveat there is this is just one part of the computing task, right? Just that FFT. But it's still not the same as like if you took a GPU saying, oh, well, I can do the compute at 5 teraflops, but the PCIe slows me down. No, that's literally how fast it'll go, right, at that task. So that's basically that the box itself is 135 times smaller, but it does 5 times as much. So if you take 5 times, huh? Yeah, basically 5 times 135 is 700. Why do what?
Multiply space times power times performance.
So a big part of this is we've got to get people to invest the time and energy into converting things to Dataflow, right? And to do that, we have to express what they're going to get out of it in some kind of real terms. So we usually do that in terms of compute and space. If you think about it, I have limited space in the data center, I have limited amount of power, I have limited amount of cooling capacity, and would I rather get one of those, or maybe say 20 of those, and stick them in a rack and have the equivalent of 20 racks of Blue Gene, right? If I can do that, it's a lot more power and space efficient. But yeah, so we usually think of these things in terms of compute per space and compute per power, because again, it's a different paradigm. If we say it in terms of runtime, right, it's the least meaningful metric. It's really more about throughput.
Yeah, I agree with you, but they're some like orthogonal metrics.
Space and power?
Yeah, some customers want to reduce space enormously.
Yeah.
Other ones want to reduce power enormously.
Yeah.
Other ones need to do it faster enormously.
Yeah.
But there could be 3 different customers and 3 different applications. And
yeah, so I'll tell you in this case why time is not one of them, right? And that's because I've got an Amdahl's law problem with this algorithm, that there's a good 1/5 of it that's just not parallelized at all. So even if I make the rest of it run 100 times faster, I only get 5x. So from the beginning, I've said, let's think about this less in terms of, okay, I'm going to get you 1x in runtime. It's going to run just as fast. It's just not going to be the size of 6 refrigerators. It's going to be the size of something you can put on a desk. So that's why in this case, space and power, but for other customers, absolutely. So for JP Morgan, for example, they didn't care about space and power. They cared about runtime. They cared about, okay, I've got this thing that runs in 8 hours, and that's just long enough to be useless from a business perspective. That means I can find out tomorrow how much money I lost today. Whereas 2 minutes is just enough for me to actually manage a business to it. So some customers do care more about runtime. In this particular instance for Quantum Espresso, I've been focused. This project is also focused on energy efficiency. That's really what the pre-procurement process, what they're looking at is building exascale sort of scale computers that are energy efficient. So they're looking at that 50x.
Look for better algorithm, but you make too many iterations to go to your eigendecomposition.
So
there are other ones where you can triagonalize first, and then the iterations are much less.
So I think in a lot of cases, obviously, we do look for changes in the algorithm. I mean, that's one of the things that's very different from.
Input out at the same eigendecomposition.
Yeah.
You sell eigendecomposition. So pick an algorithm that fits your architecture.
So in this case, we're doing things at a way lower level than the actual eigen problem, because for this particular one.
If you pick the right level, you get an advantage that's more than a factor of 5 in the.
Oh well, there's a second level to this, which is I haven't gone into it. We'll talk afterwards. I'll show you. There's a second level, but basically there's 2 sides of this. There's linear algebra and there's FFT. If we make the FFT run really fast but not the linear algebra, we get nothing out of it in a large scale. Yeah, but no.
That's the bottleneck. Don't do the FFT for the eigendecomposition. Try diagonalize it first, and there's no FFT there.
Well, in this case, the FFT is more about actually computing the matrix product itself. It's not about the actual. Okay.
I'm going to get rid of that.
Okay. Well, let's talk after, because yes, we've looked at a lot of algorithmic ways to change this. Okay, so the final thing is, all right, now I've got my actual Dataflow computer built. How do I actually deliver it? How do I get it in the hands of the people that want to use it? How do I integrate it with the Fortran? How do I get it to be a working piece of software? So what the Max compiler does after you write your MaxJ and you run it through, you do your hardware build, what it's going to give you is a binary file that contains the actual structure of the chip, right? The binary that's actually going to get loaded onto the chip itself. And it wraps that in an API. It's a C API, and it handles all the low-level details, all of the the driver and talking by PCIe and all that. So what you end up with is basically a shared object file. It's very big because it has all that binary data in it, and you have a header, and the header has just C functions, right? So I can integrate that into anything I can integrate C into, and the function calls are very simple. It doesn't have that need to copy things from host memory to device memory. It's like literally I just give it a host memory pointer and off it goes. And I've actually structured this so that I will be able to point it at the memory natively allocated by Fortran. I've literally just, there's where Fortran keeps its memory. The data's already in the order that you want it in. It's padded the way you want it, and it'll go grab it straight from that address in memory and send it over the PCIe. So we call that the simple live CPU, the SLIC interface. So it's really a much easier interface to use, I think, even than other accelerators. We also call that the SAPI, the single device API. We generally have multiple layers of those APIs, so we'll generally have like a middleware type layer that divides up the problem, handles intercommunication between the devices. We call that the multiple device API or the MAPI. And basically the idea there is it just, like I said, it allocates the problem, splits it into pieces. And then the final kind of API that's going to be very unique to us is what we call the device API. So this is, OK, now I've solved one problem with MaxJ, and I have an existing working Dataflow computer. And now I want to solve a very similar problem with a little tiny tweak. And like I said, it's not a dynamic graph. So if I make that tweak, I'm going to have to go through the build process again. But because everything is built in this MaxJ's Java-like language, it's all object-oriented, it's in a jar somewhere, I can basically go grab that jar, pick a couple pieces out of it, assemble them, and get a working Dataflow computer. That's what we call the DAPI, right, is where you're working with pre-built MaxJ components at a much higher level. So now I'll kind of move into this portion of the talk. I want to talk about a broader spectrum of the things that we have done outside just the specific Quantum Espresso project. So the best way to see that is at this address, appgallery.maxseller.com /# for some reason. This is our app gallery. This is the world's largest collection of Dataflow applications, which is, it may also be the world's only collection of Dataflow applications, I'm not sure. but there's a lot there, and it covers a lot of our science use cases. So you can see, like, just from this screenshot, right? I mean, there's things like the brain network, there's physics, there's just straight computer science, packet capture, imaging. There's lots of different examples. A lot of where this comes from is we have interns that come and they'll work with us for a summer, and they'll put together a project and put something on the app gallery. I think there's something like 40 some odd applications, and a lot of them have source code that you can look at as well. Here's an example of that sort of next level, right? Which is, all right, Dataflow computing is awesome for computer science people, but we want to put Dataflow computing in the hands of regular science people, right? That have a problem they want to solve, but they don't want to spend time learning how computers actually work, right? So a good example of this, finite difference, right? We do a lot of finite difference work. One of the reasons finite difference works really well for our technology is because of that FMEM. If you think about finite difference, the way it usually works is I have an element, and to update that element, I need to look at elements around me. And that doesn't work really well when you have a strictly data parallel architecture, right? So if I have an architecture where I have, OK, this node right here, or this CPU or core or whatever is doing a calculation on this element, and it needs to get data from a nearby element, a lot of times there's a hierarchy, right? Like sometimes if it's just the nearest thread, I can grab it from a register, but maybe if it's in a different part of the chip, I need to go through shared memory, or there's hierarchies and there's halos and all this kind of stuff, right? For us, what's nice is we can keep a really big window right there in memory on the chip. And that window is really just represented as different points in that stream of data, right? So if I think about my window, the element to my right is just the next element in my stream of data. The element to my left is the previous element. The element above me is maybe 500 elements previous, that kind of thing. So finite difference translates really well. And this was one of the first problems that we worked on for the oil and gas industry. They had to run these really big 3D finite difference models. At some point, we said, all right, there's a lot of these geoscientists have these equations they want to test. They don't want to learn MaxJ. They just want to write equations. So what we built was MaxGenFD. MaxGenFD takes Java, where the science user literally just writes their equations. They define what their stencil is, and then they say, my update equation is update at time t is this element at time t-1 times this factor plus whatever, right? They write their equation for the finite difference. And our layer on top of that does all of generates the MaxJ. It does all of the halo, figures out all the sharing when I do need to split this into separate DFEs. It does all that mechanically. It figures out how to decompose based on how many DFEs there are, all that. All those details get handled by the MaxGenFD, so the science user puts in the equations and gets out the results. Really, really basic stuff. So this was very popular with the oil and gas industry in particular. This is one of my favorites. This is an actual academic peer-reviewed publication where they measured our speed up over a similar size box, right? So these numbers, these 19x, 14x, are comparisons on a 1U to 1U basis. And what I like about these numbers is this is a real test, right? So this is not a theoretical model. This is not an Excel model or whatever. This is literally timed from beginning to end in the same kind of setup. running the same kind of algorithm, that kind of thing. And you see just this massive speed up over both the CPU and the GPU versions of this, right? So that even if I take that one U node and I start sticking a Fermi or a Kepler GPU in it, I get, okay, it's 1.5, it's 2, 3x better, right? Because I still have to deal with that issue of sharing memory and all of these things. Getting that strict data parallelism just doesn't completely magically change my world there. But when I go to the MPCX box, again, same size box, same physical space in the data center, it's 19x faster than that CPU basis instead of just 3. And then the last one, machine learning, because everybody has to do machine learning now, right? This has really been a push in the last year or so for us. There's a couple of advantages to this hardware for machine learning. Right? One of them is, just generally speaking, any kind of algorithm where I'm doing a lot of very simple computation in bulk is great for Dataflow. Right? The more branching, the more divergence, the more I sort of do some calculation sometimes, some calculation other times, that kind of stuff gets less efficient for Dataflow, because what I end up doing is essentially building 2 Dataflow computers side by side and then muxing their outputs together. Right? So basically, they're both running all the time, but one of them, the data is just getting thrown away. Right? It's not very efficient. But if I just know I'm going to go through this kind of multiplication just a gajillion times, billion times over this multiplication in some orderly fashion, that's perfect for us, right? Because we just flow right over it. But the other advantage is that because we're designing the hardware, we're not limited to the specific types. We're not limited to integer types, floating point types. I can do fixed point types. I can do 2 bits if I want to do, right? So I can change the precision of my machine learning sort of calculation to whatever, sort of the lowest precision I can get that's still reasonable and get the maximum amount of performance out of it. Right? And the other advantage is just we have a huge amount of memory. Right? It's very hard now to buy a GPU. They're starting to make them now that have more of that 1030 whatever gigs, but for the most part, the ones you got now is about 12. Right? You usually get about 12. And that limits your model, right? I can only put so many weights. I can only do so much training data because I'm limited in what I can put in that memory. We have more memory, but we also, again, have that ability to process massive amounts of data by just flowing it through in time, right? So I can do essentially my flow my data in, do my training and my inference all continuously. So I'm actually updating the weights while I'm using the weights continuously, and have it flow out. So. And you can see here, this is this is a fairly old one. We need to update this, but you can see that there's a performance comparison. This is 8 of our last generation. That's 6 pipes at 16-bit, and comparing that to 2 GPUs let me see, what is that? It's about 10x performance in terms of training time and in terms of energy as well. And obviously, training energy is a big thing now, right? I mean, if I'm trying to do machine learning on a very, very large data set, and I'm going to run a very large data center over it for a long time, then I really do start to care about things like compute per space and compute per power. So that's it for me. So what? Open it up for. Do we open it up for Q&A now, or do we do that afterwards? Okay. Yeah, absolutely. So I'll open up for questions. Yes. Go ahead.
You said for the PCIe you were able to get only about 3 GB per second transfer rate, but usually the theoretical max, if you have 16 lanes, I think is closer to 12 GB per second. Is there any reason you weren't able to?
Because we're using X8 and we're upgrading to X16 now. Okay. So that's just a hardware, and that's true for a lot of this really, is that it's just kind of up to what generation of hardware. Same thing with the Ethernet port, where we've never actually done 100 gig E. It's not because we can't, it's because to do it, somebody would have to be willing to pay for the IP core and would actually need it, and we just haven't had the need for it yet. So same thing with PCIe, when we move to X16, we'll get the same PCIe bandwidth that you get for X16, it's just we're using X8 now. Yes?
What can you tell us about the hardware, the chip onto which these things map? How are these developed? What are you using? What's the programming technique? To what extent are you actually burning silicon as opposed to downloading the way you would for an FPGA or something?
Well, it's an FPGA emulator, basically. So what it is, it's an FPGA chip, and we convert our Dataflow graph into VHDL. And then we pass that over to the vendor-designed tools. So you'll notice, by the way, I managed to make it. What are we now in? Almost to the full hour, right? And I have not said the word FPGA yet. So you noticed that? Yes, there's a reason for that. I'm not supposed to say it. Well, and I'll explain why, right? First of all, we're not an FPGA computing company. We're a Dataflow computing company. Part of that's obviously a marketing thing. But really what it comes down to is Dataflow and FPGA are two different concepts, right? FPGA is reconfigurable hardware. A lot of people use FPGAs for control flow, right? They basically build smaller cores or things, but they're still running instructions and stuff like that. So FPGA is not the same concept as Dataflow, and vice versa. Dataflow doesn't technically require FPGAs. It's not the only kind of hardware that theoretically could represent our Dataflow graph. It's just right now it's the most accessible one. So yeah, so the way it works at the low level is we take that graph, we convert it to VHDL, and there you're thinking through all of the pipelining, all of the timing, all of the scheduling, all of those details get handled by the compiler. It takes the VHDL and generates it, and then we pass that to the vendor tools. The vendor tools are what actually give us the binaries that we can then load onto the chip. And then when we go to load them, that's all loaded in software. So I have the chip sitting on the board. It takes about 1/10 of a second to load them. So for example, it's possible to do things like design a processor and, okay, maybe at the beginning of my calculation, I don't need 64-bit accuracy. I can do 32-bit. And then, oh, I reach a point where 32-bit is just not converging anymore. I'm down to that 32nd bit in terms of accuracy. And I say, okay, I want to do better. I just switch it out with a 64-bit processor, like that. Take the old one off, drop the new one on in software. And that's all handled with those CAPI calls.
And are these existing commercial third-party FPGAs? So
the latest generation of our boards is the Vertex UltraScale 9+ from Xilinx. But we've actually alternated. We've used Xilinx and we've used Altera. Again, that's the benefit, right, is that we want people thinking about their problem in an abstract way in terms of data flow. We don't want people thinking about hardware implementation details. We do all that. So if you've written your application in Dataflow for our Altera boards, and you say, okay, well, I want to do that on a Xilinx board, you can go ahead and do that. It's you take the same high-level code and just compile it basically for a different architecture. But we've extracted all those details away, and we use just basically whatever's the best chip on the market.
When I look at Dataflow, I see these big graphs, and they have a lot of crossing. How do you deal with the crossing in this? Is that
so congestion can be a problem, right?
Yeah.
So I mean, we're going to have the same kind of congestion problems that you're going to have generally routing the hardware, right? So a lot of it comes down to the vendor tools, you know, how good they are at handling the congestion. Sometimes the problem's not solvable, and you have to lower the frequency and things like that. But the advantage there, I think, if you look at a graph like this, right? So you're talking about, where was I? It's this one, right? Yeah, and you can see, like, there are a lot of places where I have these thick bands, right? And these are all strictly parallel, right? These are operations where this is basically graph viz, right? And it's putting them all at the same level because they don't have any dependencies on each other. And these are things I can physically lay out, you know, side by side and have them operating in the same clock cycle. But yeah, I mean, granted, a lot of these crossings are just artifacts of the way graph viz draws the graph. There's a big part of it. But yeah, I mean, generally speaking, if I have these two kind of wide bands, and then there's a lot of back and forth between different layers, that's a congestion problem. It's a routing problem that yeah, it just comes down to how good the vendor tools are at solving it.
So traditional FPGAs like the Xilinx board or Altera, whatever that you guys are using, are bit level configurable.
Yeah.
And they've been that way for a while because they started out as prototyping tools.
Yeah.
But if you have something like a 128-bit bus that you want to route somewhere in your design, which is pretty common. You lose, there's a lot of efficiency that you lose by routing all those signals individually.
Yeah.
Are you aware of any vendors that are moving to sort of a more coarse-grained FPGA architecture, or?
No, I mean, I personally know, so I can't fake an answer to your question, so. No, yeah, I mean, and it is fairly common. So for example, in the Quantum ESPRESSO, the buses that come out of the memory controller are 512-bit. So yeah, I mean, they get big and they get congested. A big part of that is, one of the things that we obviously have the advantage to do is it's bit configurable to the point of I can literally say, I don't want 32-bit, I want 30. I want 29, I want 15, you know, whatever is the level that you set. And what's nice when we have this really high level abstraction is it's easy to test that mathematically without having to simulate and build the hardware. So I can say, all right, a lot of times I'll make it a sort of configurable parameter. So I'll say, okay, the number of bits that are going to be used to represent my data is an input. And I can go and build this whole thing and say that input's 32, and I can build the whole thing and say it's 30. And then I can go simulate them, I can get the answer, and I don't have to build any kind of complicated machinery to figure out whether 30 or 32 bit will actually give me the answer with the precision I want. I can go test it. But then when I go to build it in hardware, yeah, I mean, I have the same kind of hardware challenges. This is more about rethinking the algorithm and the way that you do the computation than it is about some sort of novel solution to the hardware. Yes?
Are you guys able to get on the FPGAs, like for the biggest designs, without it kind of totally dropping off in Fmax or clock frequency?
So this one is, I think, 95. But at the same time, it also doesn't mean timing. so yeah, no, I mean, it varies. But again, it's the same problem. I mean, we don't have our own sort of hardware tool set or whatever. So we're limited in the same way that the vendor tools are limited, and we're limited to whatever the hardware they're producing is. So generally speaking, 95% you're pushing it, right? Because you're using a lot of the logic slices for routing as well. I had that problem with this. And the way I fixed it, right, is I took this and I changed the bit widths so they were more optimized for the DSPs. And when I did that, I got a lot more logic. And so it looks like my utilization is really low, but it's using a lot of the logic for routing. And that's how I'm able to sort of meet timing. But this is a much better picture to show it because the kernels are fatter. So it's just easier to see. Yes.
In any piece of hardware that you have or anything, what's the maximum memory to FPGA bandwidth you have?
It's generally 20 gigs a second per DIMM because it's DDR4, and I can't remember what clock frequency we run it at. It's 1200 megahertz, some called clock frequency.
Not out of the memory, but from the memory to the FPGA, and
You're talking about like FMEM?
In order to get memory data into your FPGA, whatever architecture you've chosen, what's the memory bandwidth that you have? I don't know how many memories you have.
Well, okay, so the first thing is if I'm getting data from the host to the device, it doesn't have to go through memory at all. Okay, but you're talking about from the chip to the onboard memory? That's generally 20 gigs a second per DIMM. So if I have 3 DIMMs, I can either chain them together and basically use that in like a 3-channel mode or whatever, something like, and get 60 each. Or in this case, I actually have 3 separate memory controllers, and each one is getting the full 20. Now, how fast you actually get comes down to basically the efficiency of your memory access pattern, right? So for example, in this case, I've explicitly structured the memory access so it doesn't write, it's not the way you would think of a transpose, right? Where it writes out the whole thing in a big long chunk and then reads strided where the stride is really large, because that's inefficient. So I actually have it write out in smaller pieces so that the next one is not as big of a stride. And I can control that all manually. I have actual command kernels that send 64-bit commands directly to my memory controller. And I can explicitly control every part of that process. How fast I actually get comes down to how random that access is, how batched it is. Am I opening up 8 blocks at a time and getting all the data out, or am I opening up a block here, a block there?
Question along the same ilk. If you wanted to continuously transfer data, how fast could you continuously do it using that architecture?
I mean, it's the same.
24/7. Data maximum
That's
flow
the
rate.
20 gigabytes.
Yeah, I'd say it's the same speed.
You said 20
Same
gigabytes?
speed. Because again, you have the advantage of you're not batching or caching or any of that kind of stuff. So if you can move it 20 gigs, as long as you have a 20 gig hole for it to go into and a 20 gig source for it to come from, you're fine. Now, if you have some bottleneck somewhere else, obviously you're not going to achieve that. But yeah, you could run at that full 20. It's the same thing. So for example, this will do 200 cubes a second. If I wanted to do 200 million cubes in a million seconds, I would just run it for a million times longer. But it wouldn't. At no point would I need to batch the data because the data flows continuously. So I can theoretically process hundreds of terabytes of data because the amount of data I process is just a matter of time. It's not a matter of actual storage for that hundreds of terabytes of data. Other questions? Yes.
Could you tell us a little bit more about Maxeler technology? How long has it been around? How many employees? What the funding might be? What the business model is? When you will be going into incoming revenue stream, whatever you can, more than that?
Boy, I don't know how many of those I really can or should answer. I mean, I can give you a little bit of the history. We've been around for 13 years. We have generally been invested in by our clients. So that sort of frees us from, we don't have massive amounts of debt or anything like that. Basically people work with us and they realize this is a technology that needs investment and development, and they invest in us because they know it has a future. And for a lot of these people that we're working with, the amount of money involved is not great for them, but it has the potential to really, produce sort of longer term benefits down the road. So that's why they invest. I'm not really sure what more details I could give you in a public setting.
Is the business model to be selling products, selling boards, licensing technologies, licensing IP?
I mean, we really do kind of all across the board. We very rarely do just like a pure hardware sale or a pure software sale. There's usually consulting services kind of bundled with it. So a lot of our clients, because they're tiptoeing into the water on a new thing, right? So it's not something where I can just drop a box off at your door and let you work with it. So generally speaking, it's kind of a three-prong. We sell the hardware, we sell the software, we sell the service of porting things into the software. What we're finding is that's becoming less a part of the business because we're now getting to a critical mass where more people are wanting to do it themselves. We now have a lot of clients that are saying, no, teach us how to do it, give us the box, but our proprietary business logic, we don't want to give you. We want to do that on our own and own it, and have the knowledge developed in-house to maintain it. That's something that's happened more recently. So the business has always been kind of a mix of hardware, software, consulting services. Really all three, and it's very rare that we sell one without the other two.
And how did you get involved? Because this is a far cry from actuary. You seem to understand.
I'm a far cry from the ordinary actuary.
You certainly handle the buzzwords and the descriptions.
I work with a lot of really smart people, and they do their best to make me look good. No, I got into this because I've been working in finance. GPUs had started to get very popular in finance. It's becoming kind of there's a lot of sort of technically unsophisticated people trying to do sophisticated things. It can be frustrating. So I looked at it and I said, all right, I want to get on the next technology that's not crowded. And that's why I chose this. I said, I want to find a company that is using a technology that nobody else is using in a really experimental, cutting-edge way in finance. And we do have a very substantial finance business, so that's really how I got into the organization. But I've always been a kind of amateur hacker in one way or another, and I've carried that in every profession.
Architectures have existed since the late 80s, and data languages since the early 80s. I'm sort of curious. For instance, if you guys had used IF1 and IF2 as intermediate forms.
I'm not familiar.
Yeah, and the thing is, the guys over at Livermore, this little company called Digital Equipment at one point in time, and I think Colorado State, they did the Sisal programming language, which was a very interesting language in many respects, but the problem was it simply could not compete with the mass of existing code.
Yeah.
And that's independent of the two different lines of work done at MIT beforehand, one of whom I was trying to get to come here because he's now at Carnegie Mellon. We're trying to get him to talk about Carnegie Mellon, independent of Dataflow as well too. So, there's all kinds of interesting things that, people did build Dataflow hardware, and friends of mine locally have run on Dataflow machines, and they ran into all kinds of interesting questions that were not really resolved at the time, like structures and all kinds of other stuff like that people like. If you modified merely one element of say an array as example, does that then invalidate the whole array? They had not thought about that.
Yeah.
At that point in time. So
it's a common thing we hear from a lot of clients. Is like sort of we've tried it, right, but we've never actually gotten it to produce a number that works. And a lot of times that's the advantage that we bring in is that, because we've just really gone, after doing this for 13 years and sort of knocking around all the things that do and don't work, there's a lot of just really practical knowledge built into the compiler. So that, we make it to the point where, yes, people can actually get numbers that work out of them.
Like, for instance, you use the phrase simple code. You realize that one of the major benchmarks was named simple.
Oh, I did not know that.
Through the 80s, the 70s, and the 60s. And in fact, it was a finite difference code, is my understanding. And it was implemented in a variety of languages. And, there are a couple of books about the Dataflow stuff as well, too.
Absolute question.
No, we're chatting about the whole field.
I'm noticing
There are questions.
absence of a question. He has a question mark in the first 7 words of his what he's going to say.
So are any of your problem spaces using enough cycles that it would actually be interesting to compile it into raw hardware instead of going through the FPGA step?
I think that would be interesting on everything. It's more a matter of money, right? Like yeah. You're talking about like building an ASIC from it, right? Yeah.
It's just push a button, right?
Yeah, no, absolutely. I mean, I think there's again, that's why I say there's nothing about, you know, the hardware necessarily. I think it'd be interesting to do that in every case, but most people are not looking to spend tens of millions of dollars to put out a chip. And the advantage really is you know, the way I always sell this to people is speed, the speed of hardware, not as good as an ASIC, obviously, because nothing's going to beat an ASIC, but it's very close in some ways. The speed of hardware at the design speed of software. And most people still need that design speed. They still need that ability to, especially like, say, a finance client, they introduce a new product or there's a new twist on some derivative and they need to change one little thing in a model. I can't do that if I already have the chip, right? But I can do that really easily if I'm doing everything in software. And the only real time-intensive part is the place and route. You know, which if I have a good simulator, I should only be doing once, right? I basically do that when I know it's going to work. And then it's more a matter of just figuring out all the issues of place and route, like what frequency and how to optimize the resources and things like that. Yes?
I'm kind of curious. So my understanding is everybody who's been coming to you has something that they're already doing that they now want to do with you. In your experience, have the people coming to you been coming to you with mostly CPU code or GPU code to convert?
We see a mix of both. I mean, obviously, my preferred starting point is going to be CPU code because I'm not going to keep most of it anyway, right? I mean, I'm going to need to really understand what it's doing to map it into a different paradigm. And I'd rather do that without the overhead of figuring out the just multi-core and the way the parallelization works among the threads and all that. It's just easier to figure it out. But so, for example, there is a GPU version of Quantum ESPRESSO. Right? There's a CUDA accelerated version. And I haven't really looked at it, right? Because the way that you would structure it's completely different. First of all, you'd use a library, which I wouldn't use. But you know, like I said, you'd start by moving everything into memory and working on it in pieces and batches, and it's a completely different paradigm the way we're doing it. Actually, what's interesting is the vast majority of my code, if you look at the code, the FFT is a tiny little part because I pulled that out of a library. We already had FFT built. I had FFT done, all 6 of the FFTs done the very first day. It's 1 line of code each, very simple. The tricky part is the sphere and the circle. That's the tricky part, right? Because you're moving through that cube, you hit the sphere, and you get entered at different points, and you come out of it at different points, and you have to keep all that in memory. Huh?
It's a real tensor.
Yeah, very much.
As opposed to the AI types, these are rank 1 matrices.
Right, it's not a block.
Those are much simpler.
Right, it's not a
real
block of memory.
3D tensor.
Right, and so for example, with some of these the GPU accelerated, that's a problem because GPUs like their memory to be nice and rectangular, right? They like it to be nice big blocks. So yeah, so it for us, we think of it more as, you know, imagine I've got a cube and I've got a sphere in the cube and I'm moving through it like an ant, crawling through it cell by cell. When do I pop in and out of the sphere? And I have to know all of the different dimensions of all the different points of the sphere to be able to do that. That's really where all of the real work was. And none of that has any analog in CPU or GPU or anything else. So when I'm starting with code, it's easier for me to look at code that's really basic and says this does an FFT and start from that. But yeah, we have clients that come to us, generally speaking, I mean, they're more likely to come with CPU code because they're more likely then to need performance, right? They're more likely to have a problem that, whereas, you know, if they've invested the money in a GPU project, okay, maybe I don't have the performance I want, but I put a lot of money in it and it's already better, and maybe I don't want to do any better than that. But it's easier if you're starting from far behind. It's also easier if you come in with few assumptions. The best things are the clients that come in and say, I know what I want in a qualitative sense, right? I need a picture that makes sense. So for our seismic modeling people, for example, I need a picture of the oil field that physically makes sense, right? I don't need 64-bit precision. I don't actually need to know that red is red, you know, 100.0001 instead of 100.002. You know, it's red, right? I'm going to make a qualitative decision. those are the best clients, right? Because those are people we can come in and say, let's open up your algorithm, open up your thinking, talk about precision, talk about maximizing your qualitative result for the minimum amount of compute time and energy and space. Oh, yes.
Yeah, so I was just gonna ask about AWS. Have you guys run a lot of stuff on the AWS FPGAs yet? If you see any like performance problems or anything like that?
So what's nice about AWS, we actually partnered with them on that. We had sort of, they'd been talking to us long before that was announced. So AWS has released an F1 instance. I think right now it's only available in the US region. I'm not sure. That instance is the same chip as what we're using. It is not exactly the same, the whole board, because Amazon likes to do things like protect their PCIe pins. You do not want to give someone raw access to PCIe pins in a data center. That's a really bad idea. But the idea is the same. So we're not quite there yet, but it should be happening in the next month or two, where we'll have now a version of the compiler that will compile for F1. So you'll take that data flow. It's the same MaxJ, it's just you'll flip a switch here and there to say I'm compiling for a different architecture. I believe Amazon's model is you send them the VHDL and they build the FPGA image off it. But we will have the ability to run pretty much anything that's run on the latest generation of hardware should be pretty easily portable into AWS. And that's coming probably in the next month or so.
If you're a student, or if you're not a student, we usually go to dinner afterwards, and I'm hungry. So.
As am I.